Now, what I have here, I've gone ahead and let me bring up T-Square. Hopefully all of you have been able to log on to the T-Square site and see some of the materials I uploaded. If not, I'll show you how it works here. Here's our Shenzhen section, and let me assume that I am a student. This is what you would see if you were a student instead of somebody with editing privileges. Okay, first of all, the syllabus is basically everything that we talked about the first day of class. I went ahead and put a PDF copy of the syllabus with a lot of the extra things that you need on a syllabus to describe a class formally, and you should be able to load that up like so. There it is, sort of a perspective list of topics to cover. I'll be changing that a little bit. And then grading scales, other requirements.
So we can download it from T-Square.
That's right. That's right. This is available as a PDF. Everything I'll show you on this site is downloadable by T-Square. So then you go to resources. I think I've got 3 folders here. There they are. I've got lecture material, notes, and papers. So under lecture material, I'll put visuals and things that I share up on the computer here so that you have a record with it if you didn't get to copy it down in your notes, or if you were trying to memorize it instead of writing, however you record information. And like, for example, I have the slides that I shared that first class period. As you can see here in Shenzhen, China, we're a little bit export bandwidth limited, so this relatively small PDF file is taking a very long time to load. My apologies to all the students here. If you ever need it on a thumb drive, just come by my office. I don't think the DL students will have to worry about that. Anyway, you know what those look like. That'll load up eventually. There we go. Let's look at this guy rolling on something else. So if you go back up to the root directory, there will also be another folder called Notes. These are going to be supplemental notes, usually my own personal notes that I've typed up for the class. It won't be available for all lectures, but there is a little bit of material, for example, talking about some of the introductory things that we mentioned on Monday's class. These are the topics on energy harvesting and energy of computation that we mentioned, mostly energy of computation. And they've got some of the graphs that we talked about on there. And then the other thing that you can look for, once again, here's the slides. Make sure you download that if you didn't get a good view of what things are. Then since this is an upper level graduate class, every lecture will also have a research paper that's come out in the last several years to kind of review with material in it to talk about, you know, whatever topic that we need to. For last class period, I've uploaded 2 papers already. Last class period, I uploaded a nice paper by Kumi, the guy that made the big chart with the computational analysis and the energy analysis of computing. Now keep in mind in that paper, he's mostly talking about high-end computing or desktop computing, microprocessors in general. And that's good, so I've got his paper on here. Let's see what I named it. Oh, very peculiar. Okay, so here's his paper. It has a very difficult to understand title because I got it off of IEEE Explorer. I probably should have changed the title there, but that's Kumi's paper. It's a real nice look back on the history of computing and is talking about energy analysis. If you think about it, I always used to tell my students that if you want to know what the future of electrical engineering holds, you always look at the material science people and the device people. Because what they're doing in the laboratory, once it moves out into production, eventually bubbles up and affects everything that we do, right? It affects how much big data you can process. It affects, in our instances, how much wireless communications you can do, how many sensors can you build, how long will the battery last on a mobile device. It's really this energy revolution more than anything in terms of devices and computing that has led to things like smartphones in the last 10 years. You know, there's no magical algorithm that made this thing work when the first iPhone came out in 2008. All the algorithms, all the communications theory, the programming principles, all of that was invented 50 years ago. And it's really the low power enabling of the battery and the computational platform that's really enabling all that. That was the breakthrough. And as we saw, that was a steady progression through time that continues even to this day. Now, if you think about the computer industry, think about the device makers like Intel and AMD and all these big companies that make chips and especially high-end processors. They're selling hundreds of millions of units of those things. And a lot of the high-end devices are pretty expensive. You charge $100 a pop for them if you wanted to, or more. So that means that, you know, that industry alone is bringing in hundreds of billions of dollars, and they've got the really deep pockets to do research and development, to research new materials, to research new processes, to invent like the next smaller scale size of integration for making chips. Everybody else kind of has to live off of their table scraps, right? So for example, in the industry that I'm in, that I work a lot with, RFID, the technology that they're using is really like 5 or 10 years old CMOS technology from the microprocessor people. You know, you had to wait until it was mature and cheap, because RFID doesn't have nearly the margin that microprocessors for computers have for just bringing in a whole bunch of money and being able to invest it in a new generation. And you'll find a lot of other, you know, if you go into microcontrollers and low-end embedded computing, they're doing the same thing. They don't have the big volumes to invest in their next generation. Instead, they have to lag what the microprocessor people are doing by a few generations and kind of live off of what has become cheap or deprecated technology in the world of computer processes. So all that to say, take Kumi's paper with a grain of salt. We're not going to do a lot of high-end computing in this class, but really that arc, that historical arc all the way back from the 1940s is what we're interested in. And versions of that technology, in many cases, still from 5 years ago, are what we're going to be anticipating in terms of our sensors, our wireless devices, our passive chips, our RF hardware that we use to read things. So it just gives you a nice historical perspective. The next paper that I put up here is a nice review article from the Microwave Magazine, IEEE Microwave Magazine from a couple of years ago. My student Chris Valenta wrote it. He's now Dr. Valenta. He works for GTRI. And he did such a wonderful job of it. They gave him the 2014 Best Paper Award for the magazine. And it's a really nice overview of wireless energy harvesting. This is going to encompass our first couple weeks of this class. 2 to 3 weeks of discussions will be centered around wireless energy harvesting and getting not only just how to get power from point A to point B in terms of communications, but also to do energy harvesting for driving computation as well. So yeah, do you have a question?
So what's this paper about? Wireless and communication?
So the paper itself, let me go ahead and bring it up for you. And close down these notes. And here we go. There. This is there's actually a final proof copy of this on IEEE Explore if you're familiar with that site. If you're logged into the Georgia Tech VPN network, you can get to that site and all the papers for free. Yeah. Many institutions would kill for that kind of access, but you get it for free as students of Georgia Tech. This is actually a proof copy that we have. So it's basically an overview of wireless energy harvesting. And we'll talk a little bit about this paper today. I've got some visuals from the paper that I'd like to discuss after we do antennas and circuits, which will be the first half of our discussion. We'll go until we hit the 45-minute mark, take a 15-minute break. So that should happen at about 1:45. We'll come back at 2, and then we'll do another 45 minutes. So it's just a nice overview paper, good for an introductory. If you don't understand everything in it, that's okay. There's a Smith chart in there. How many of you have seen a Smith chart before? Raise your hand. The physics guy, yes. Good. Good, of course. The electronics guy? No?
A bit of it, I just heard about it.
Yeah, yeah. It's kind of like the abacus for electromagnetics engineers, but it's actually very useful. Look, there's a Smith chart. Anybody seen that before? Yeah. It's okay if you haven't. Just skip by that section. But there's some really nice analysis here to kind of introduce you to the topic. And I think that's it for T-Square. Those are the 3 folders: papers, notes, and visuals. And I'll keep updating this with every class period that we meet. So do you have any questions? Any questions you didn't ask about the syllabus or the course workings from the first class meeting? No? Okay, let me go to this real quick. I have just a handful of visuals. Slideshow. One in particular I wanted to go back and look at. This is a much cleaned up version of the radiation solution that I scratched on the screen last class period. I just wanted to wrap it up and make a couple of key points. So what we have here, if you'll remember, is, see if my pointer's working. Oh yeah. This is the H field and the E field, the electric field phasor and the magnetic field phasor of a propagating wave for a Hertzian dipole, which you'll recall is a tiny bit of oscillating current in space that exists almost practically at a point in space, magnitude I, current I. And there are a couple reasons why I put this on the board, not just to scare you and think, oh my gosh, we're going to do a lot of field theory in this class. I wouldn't have any students left if I did that, right? This is not primarily an electromagnetics class, but I'm an electromagnetics teacher, so, you know, me and the physics guy enjoy this stuff. So anyway, the only difference here in terminology, we're looking at the field solution, a point R away. This is my point of observation. And because these are field quantities, magnetic field has units of amps per meter, electric field has units of volts per meter. And this is going to be a function of your points of observation. In the spherical coordinate system, R is your distance from the origin. We'll call the location of our dipole the origin. And if there is a z-axis pointing up, if this is a z-directed current, the angle that this point of observation makes with the z-axis is theta. That's our elevation angle. Keep in mind that this is what electrical engineers use as theta. They use theta to denote elevation as measured from the z-axis. If you're a mathematician, what do you use? All the math people use phi. They actually reverse it. So for us, if you drop a projection down onto the xy plane, the angle that that projection makes with the x-axis, we call that phi. The mathematicians call it theta. It doesn't matter, right? You're all engineers. Part of being an engineer is being able to adapt to whatever convention that you're using, not just being hopelessly lost when somebody changes a variable on you. So I don't think anybody will have a problem with that in this class. But I just want to point that out, that there are some differences. And then, of course, these are vector quantities, right? Electric field kind of tells you how much force is going to be on an electric charge if you put it at that point. And magnetic field tells you how much force is going to be on a moving charge, right? Yeah. So these are vector quantities, which means when you get to this, in the spherical coordinate system, when you get to your point of observation, there's going to be a unit vector r hat, a unit vector theta hat, and then a unit vector phi hat, an orthonormal basis of unit vectors. And so that's what these terms are here. You see, these terms are decomposed into their unit vector components. So we have H field, which is only points in the phi hat direction. You have E field, which only points in the theta hat and the r hat directions. And I've ordered them such that we have sort of order 1 over r to the 0 in this column, just like last class period. Order 1 over r in this column, and then it's r to the 1, and then order 1 over r squared. So I thought this was a little cleaner way of depicting what I was depicting last class period. Everything's the same otherwise. The only difference between this treatment is that I'm using wave numbers instead of wavelengths. K is the wave number in radians per meter. It's really just 2 pi over lambda. And we already talked about before how lambda times times frequency is equal to speed of light. Okay, and the point of covering this was to draw this distinction between near field and far field. Everything scales in electromagnetics with respect to wavelength. If Kr is less than 1, particularly when it's much less than 1, that is when r is much less than 2 pi over, lambda over 2 pi, then these 1 over Kr terms are going to dominate. And this field solution in here, when this starts to dominate, we call this the quasi-static solution. What does that mean? Well, remember what a Hertzian dipole does. It's moving charge up and down, up and down, up and down at some sort of frequency. That means if charge is moving, that means positive charges are depleting in one region of space and they're accumulating at another. And then that's reversing. So first of all, you're going to have some inductance due to that, right? Because you've got a current moving and there's going to be magnetic fields swirling back and forth around that. And then you also have kind of like a little capacitor also, right? Because you've got charge separation now, and that's going to create a dipole moment. And if you're familiar with physics, you know that dipole moments fall off, the fields fall off 1 over r squared. So these inductive and dipole moments, now keep in mind also, there's also an additional order 1 over r term out here in both the H and the E field already. So when we say order 1 over r to the 0, that's really order 1 over r in terms of attenuation, then 1 over r squared, then 1 over r to the 3rd as we move along. So we call these quasi-static because really what you can almost get these exact expressions from studying the dipole moment of a DC capacitor with charge separation on them, or a DC current, a magnetostatic current that's just flowing in a small region of space. We call them quasi-static because really this is an oscillating system. This current is going back and forth and back and forth. But the magnetic field is circulating around And it's essentially like taking the static solution and slapping a cosine 2 pi ft, an oscillating term next to it. That's not true about these terms over here. These terms are radiated fields. And these start to dominate when you move away from the near field, when you're more than a wavelength away typically. Then these other terms on the right, you can neglect them. And these are your far field terms. And we had a nice discussion last time about how these terms over here are the terms that you would deal with in a HF RFID system, the kind of turnstile reader at your subway station, or often a access pass, anything on a badge where you have to swipe the badge or wave it in front of the bus or your entry port. And part of that's because we don't want those types of application using far ranges. You don't want, if your badge has a special secret access code on it that allows you to get into your protected building, when you're over across the street at 6,000 having lunch, you don't want to accidentally set it off and then everybody run into your building, right? So you want that tight coverage. And of course, these terms over here are your far field terms. So I just thought that was a nice clarifying discussion to put it on actual some typeset equations. And I'll go ahead and get out a PowerPoint for the time being. Go back to OneNote. Okay. One more point of order before we get into our next section. So the way that the schedule in Shenzhen works out, we normally have class on Monday and Wednesday, but this Friday is unique, right? In order to get all of your lecture hours for taking a 3-hour course, we have to do one Friday class, Friday at 1 p.m., and that's this Friday. So I was looking at the schedule, I was like, well, let's make a deal, okay? I was not planning on doing a lot of background review for radiation theory. We are users of antennas. We have to understand basically how they work, but I'm not gonna, this isn't an antennas class by any stretch. So I don't want you all to have to, become experts in antennas, which is sort of a class unto itself. However, it is very helpful to understand the fundamentals of radiation and electromagnetics. We're going to talk about waves in order to get used to the terminology that we talk about. So to that end, I wasn't going to cover it, but there are 3 background videos that I'd like for you to watch at some point during the next week. These are available on YouTube on my Prof. Durgin channel. And they're listed by module. There's wave 01, and that's entitled Maxwell's equations. There's wave 02, that is the Helmholtz wave equation. And then there is wave 03, and this is just a discussion of plane waves, which solves the Helmholtz wave equation. So this is as electromagneticsy as the course is going to get. We're not going to do much beyond this. Really, these are review videos. I think this one comes from either my SATCOM class or antennas class. These two actually come from my undergraduate class. If you go ahead and watch those, if you're really familiar with the electromagnetism, like the physics guy probably is, then you can watch it in chipmunk speed really quickly. And if you do that, then we do not have class on Friday. Is that good? I don't want to overload you with a bunch of work. because I've got a lot of lectures on YouTube, and one of the problems, like in my SATCOM class, for those, I forget who here is actually in there, but I'm basically flipping that class, so we're using the regular scheduled time as a meeting period for recitation, and do it just course mechanics, working problems, doing illustrative things like that, and then they have to watch all the videos outside of class. Now, of course, if you're getting 3 credit hours for a course, then that means the typical workload is you have 3 hours of instruction in person with your instructor, and then you've got 6 hours per week of studying, reading the book, working homework problems, talking to your friends about the class, whatever that entails. That's in theory the workload. So when a professor goes and starts flipping the class and starts like making you meet for 3 hours a week, 3 or more hours a week, and since we're in a compressed semester, it's probably closer to 4 hours a week here in China. 4 hours a week, and then you start assigning all these videos, 3 hours worth of videos here that you have to watch, and then you also have to do homeworks and things like that. It starts to get kind of onerous. It's too much for the student, so you can very quickly overload a student. So that's why I figure if you watch, this is like maybe 2 or 3 hours of video, mostly review, we'll be able to relinquish one class period so that you do not have to come on Friday to this class period. I am making my SATCOM class neat. And as far as homework goes, I haven't put it up there, but I imagine by the end of the week I will have assigned a homework number 1. I'll put it on T-Square. I'll send an email notice about when it appears as well. And I usually give students at least a week to do the homework. I'll give you a due date. Whatever the due date is for the Shenzhen students here, the distance learning students will have that plus another week since they are on tape delay. So just keep in mind, if I say a deadline without qualifying it, it's for you guys here in Shenzhen. Add 1 week if you're a distance learning student. Okay. Any other questions? No? Great. Great. So, okay, so what we're going to do now is talk about how antennas behave in circuits. Let me bring up my electronic notes here. I always like writing. When I'm in Atlanta, I always just draw all my lectures on the chalkboard. I don't like PowerPoint presentations. They're kind of a necessary evil in some ways, but I think it's important for the instructor to kind of slow themselves down to the speed of note-taking that their students have to do in order to be understood and to be remembered. You can just blast through too much material when you have it all on PowerPoints. So anyway, we're going to start off by viewing how does an antenna behave as a circuit, in a circuit. How do you model that? Because for a lot of you, you've never had an antennas class. Has anyone had an antennas class before, in any form? You've done some electromagnetic radiation?
Electromagnetic waves.
Oh yeah, okay, perfect. And you covered the radiation equations in that class?
Yeah, the dipole.
Yeah.
The magnetic, I forgot the.
No, A, right? A vector. Magnetic potentials.
Yeah,
Oh yeah, that's good stuff. Good stuff. We won't be doing anything with A in this class. So, we do it in my undergraduate antennas class. So yeah, and that's okay. If you don't have any background in antennas, if you just understand a circuit, you can understand a good bit of antennas. We're going to talk about circuit modeling of antennas and how to track power in wireless systems. Because the way that we talk about power, most RF engineers and most people in general think of transmitted signals in terms of power. How much power do you need? How much power are you using? How much power are you going to receive? most of our hardcore electromagnetic analysis is in terms of E's and H, or voltages and currents. Voltages and currents are kind of somewhere in between, is what electronics designers like to deal with. And so we're going to basically talk about how do you span those worlds, and how do you track how power gets from point A in an antenna to another antenna at point B, which will lead into a discussion of link budgets. So that's going to be our first part of the lecture here. And then we're going to talk about some electronic devices used to harvest RF energy. Once you get the RF power to an antenna, how do you convert it into usable DC power? And then next week, when we meet again, we'll start off with link budgets and talk about link budgets, both conventional radio link budgets and also something that resembles the radar equation. How do you bounce power between two places? Because we'll need to know that when we get into things like backscatter and some other forms of communication that take very little energy but still send information over potentially a very long distance. Okay. So here's our system that we're going to start off with. We have a transmitter, which from here on after I will just abbreviate as TX. We have the generic symbol for an antenna, TX antenna. Looks like a bent coat hanger. Harkens back to the old days of RF when you could just bend a coat hanger and make it pick up the radio station that you wanted. And then you have a receiver, which I will hereafter abbreviate RX. Okay. Now, the first thing to realize is that these are some abstractions. These are block diagram depictions of radio systems. If we delve down another level, we can describe them in terms of circuits, right? V's and I's. And of course, if we go down even further, we can do field theory. But we're going to just stop at V's and I's for now. A transmitter is really just a source. It can be modeled as an amplitude of a sine wave, and it has an impedance. Let's call it Z sub S. Let's make it a box. It doesn't necessarily have to be a resistor. And then, when it's used as a transmitter, an antenna behaves as a load with some impedance Z sub A. Now notice here I put squiggles on top of them because, again, we're talking about phasor quantities. That's how I deal with phasors. I put squiggles on top of them. Some books do bold, some books do script. It's easier to just put squiggles when you're drawing on them on the board. And a transmit antenna essentially just acts like a dumb load. Antennas, for the most part, are pretty linear. There's not that much you can do to an antenna to make it nonlinear, unless you transmit at really high power levels, tens of watts in many instances. In this instance, then you get solder joints on the antenna that can rectify, and if your antenna is not very well made, it can sometimes not look like simply a Z sub A type of load. But for all the problems that we're going to work in this class, it's just a constant. And that's my circuit for transmit. My circuit for receive is a little bit different. When a wave strikes an antenna, that antenna becomes a source. It maps an electromagnetic wave down to a voltage. And so in this scenario, I'm going to call this VA prime. It's going to have an amplitude. And it's going to have an intrinsic impedance, Z sub A. And then the receiver is usually something that acts like a load Z sub L. It can be complex or just purely resistive, but we'll represent it with a complex Z sub L. And here's one of the interesting things about antennas. Antennas, because Maxwell's equations are linear in a simple medium, which is what we model free space as, then it turns out that they are also reciprocal. means that if you take an antenna as a transmitter, its radiation pattern will be identical to its radiation pattern as a receiver. Yeah. So that means two things. If a transmitter antenna focuses power in this direction twice as well as it focuses in this direction, then when you turn around and use that same antenna in the exact same orientation and location as a receiver, that means it will receive in this direction twice as efficiently with twice as much gain as it does in this direction. That's one of the consequences of the reciprocity theorem. The other consequence is that the impedance that it presents to the circuits are the same. These are the same if they're the same antenna at the same frequency. So that's nice, because that means that basically if you go up to a network analyzer and connect an antenna to it, and you sweep the S11, that is, you're looking at the reflection coefficient, you're exciting the antenna and see how much power reflects back, and that basically traces out what the impedance is, Z sub A. If you do that, you're using the antenna as effectively as a transmitter. But when you go to use it as a receiver, you've already characterized how it presents itself to the receiver network with that same Z sub A, even though you're no longer exciting it anymore. You're exciting it with an electromagnetic wave instead of a source connected to its terminals. Okay. So now that we have the background, let's talk about how to couple power. First of all, at the transmitter, let me repeat my circuit here. V sub S, Z sub S as my source, connecting to an antenna that is Z sub A impedance. This transmitter is capable of supplying power, right? And if I use my circuit theory, P sub T is equal to 1/2 the real value of my voltage across my antenna times my current across my antenna complex conjugate. Make sure the complex conjugate is there. I see it's not in one of the notes that I have. Just make sure that that's there. And this is good because we're just taking V times I, which we know in DC is power, and then that 1/2 has to be there because we're doing time averaged power, right? When you're talking about the peak values of sine wave, this is the peak amplitude of a current, of a voltage. This is the peak amplitude of a current. Well, that peak amplitude is only maintained for an instant in time. You actually have all the values in between as well as this oscillates up and down and up and down. So if you average over a period, it's equivalent to taking the peaks, multiplying them, and dividing that by 2. Hopefully you've all worked through that calculation at some point in your life. Okay, and for this circuit, if you spell it out, and here we're going to use Z sub S, of course has a real source and a reactive imaginary part. And Z sub A has a real resistive part and a reactive part. So if you do that, then this quantity becomes Vs squared R sub A times 2 magnitude Zs plus Za squared. This is a 2. Put a squiggle there. Okay, this is just basic circuit theory. I'm using basically my voltage divider to get a voltage across here, and then using Ohm's law to figure out ultimately how much power is going through that load. There's nothing new there. Now there is sort of a bookkeeping thing that we have to do. What should I make Z sub A to get maximum power transfer? Yeah, for max power transfer, the thing you learned in your first circuits class, This is achieved by making a conjugate match, right? ZA is equal to the complex conjugate Z source. That gives you maximum power. That's not the maximum voltage out of the antenna or into the antenna, but that gives you maximum power. That means you'll get as most power as you possibly can from that source into the antenna. And if that's the case, then that source power that you can transmit maximally is Vs squared over 8Rs. And of course you can see that fairly readily because Vs in the maximum power transfer condition, the reactive components cancel, so all you're left with equivalently is R sub, yes? Yeah, that's right. R sub S and R sub A. This is going to be Vs over 2 if you use your voltage divider formula. Power over a resistor is Vs over 2 quantity squared divided by Ra, and then you got to do another 1/2 because they're sinusoidal quantities, so that's how you get Vs squared over 8Rs. So we call this source power. This is what the source can provide if you match it. Now, transmit power is the max power that can be radiated outside of the antenna. And we can relate these now by just using basically casting PT in terms of PS. If we rearrange the previous equation on the previous note in terms of PS instead of voltages, you basically solve Vs squared is equal to PS times 8Rs. Arrange this equation here. Then we can recast that previous equation as 4Rs times Ra over magnitude Zs plus Za, quantity squared. This quantity, as you can see, if you've got real valued positive resistance values, this value is always less than or equal to 1. That makes sense? Whatever I can maximally supply, I'm not going to be able to transmit more than that. I can transmit less than that, though, if I'm not conjugate matched. You see, if this is conjugate matched, then Ra, this becomes Rs, which is really Ra. The reactive components will cancel. There's another Ra. I get 2 Ra. Quantity squared, that's 4Ra. This becomes Ra. The whole thing turns to 1. That's the only way to get 1. Now, the question is, if I've got P sub S available and I'm transmitting it down a cable to my antenna, and my antenna is not radiating all of that power, where does the rest of it go?
Losses.
Could be loss. What kind of loss? Let's pretend I have the world's perfect cable. I've connected a coaxial cable to an antenna. It's completely lossless. I send a watt of power, but when I go and I measure the antenna, I only get, when I integrate over 4 pi steradians, I only get a total of 1/2 watt of power. Where did the rest of the power likely go? Well, there's 2 places, right? One is the answer that I'm getting at this lecture, and then we'll talk about the other one a little later. The first place it can go is just a reflection. And that's really what this loss represents, mismatch loss. I am reflecting power because I am not matched properly. Reflecting power back to the transmitter. And the other thing that you could be doing too is that your antenna may not be very efficient. It may have a low radiation efficiency. That is, I'm coupling power into the antenna and it's trying to radiate out. But maybe there is something about the antenna. There's ohmic losses because you can't make antennas out of superconductors. Likewise, there's going to be some dielectric materials nearby. Those also can provide loss to an antenna in the near field. And so that's a different ball of wax. And in RF engineering, we tend to account for that in a different term in our link budget analysis. Usually what we call a gain pattern in antenna and RF engineering, that's where you lump radiation losses, radiation inefficiencies. Here we're just talking about antennas and circuits, and so this is really a mismatch loss. We're not efficiently coupling power into the antenna. So that's at the transmitter. What about at the receiver? Well, here, recall that I said this looks like a VA prime, some sort of complex antenna impedance Z sub A, and it connects to a complex load Z sub L. Once again, I'm going to break Z sub L out. The real part I'll call R sub L. The reactive part I'll call X sub L. And if it's the same antenna, it's going to have the exact same impedance. We have transmitting between two dipoles or two dish antennas, or as long as they're identical and they're in free space, it should be the same. Okay, so this is the scenario I have. And of course, if I am conjugate matched, then that means, of course, that ZA is equal to the complex conjugate ZL. And I get this wonderful PL, my load power into the receiver is equal to an equation that looks very similar to our previous equation, except now I've got VA prime squared instead of my source VS squared. And under this match condition, this simplifies to VA squared over 8RL. And I define this to be received power, P sub R. This is the maximum amount of power that you can suck out of an antenna, right? Under the matched condition. So here's another question. Let's say if I've got a matched antenna, I can receive 1 watt of power. But I take my antenna, I just stick it up a receiver without paying attention to what the impedances are and everything. And what I measure is 200 milliwatts instead of 1 watt. Well, something is mismatched. Where did the power go? Where did it go?
Because of the mismatch, it reflected back.
Yeah.
Some of the,
Where does it reflect to? See, in the transmitter, it was very obvious to say where it reflected to, right? Because you got a cable. You send power down. Oh, it didn't have anywhere. It came back. What about as a receiver? Where does the power go?
reflected to the air.
Yes. It re-radiates. It re-radiates according to the pattern of the antenna in every direction, weighted against the gain pattern. Now that's a problem. You've just wasted communication power. Although we're going to show later in the course how that's actually a benefit. You can actually communicate with that power. Because you didn't have to have a source. You didn't have to have a source connected to the antenna. You're radiating power, believe it or not. So now let's go ahead and do the same thing we did for the previous thing. If P sub R is the maximum possible received power, and I have a mismatch, my actual power, my load power, is going to be 4RL RA over magnitude ZA equals ZL squared times P sub R. Again, this is what I would call a mismatch factor. It's always less than or equal to 1 for passive devices. And it represents how efficiently you're coupling power from the antenna that's available into your receiver. So to summarize, we've actually got, and then we'll go ahead and break because I'm already over the time that I said I was going to take a break. We basically have source power, and that becomes, when it's connected to an antenna, transmit power. And there can be a mismatch. You radiate, and you get P sub R, which is received power. And then ultimately there's load power available from that, with a mismatch lost here. So you now have every tool that you need to solve for power in the system, except for an explanation of how does PT go from here to here. And that's what the Friss free space equation or the link budget equation with realistic losses is for. We're going to talk about that next week. So we'll fill in the gap here. But you got to start by understanding how the system works and how our terminology plays out in an electrical system. So I'm going to hit pause, and then we'll do a quick example or two about this, and then we'll get on to some energy harvesting circuits, which is going to be basically the load that we plug into a lot of these electronic circuits. Okay, welcome back. Before we do an example, I want one more formula that's very useful, and this is only, or most commonly used on the receiver side of what we're talking about. So again, we have VA prime, which you never measure, by the way. Keep in mind, this is an equivalent circuit, right? You can only measure what's at the terminals of your antenna. In fact, there may not be a physical voltage VA prime that corresponds to anything on the antenna. An equivalent circuit is really just that. It's an equivalent. It's not a physical representation of what's happening. It just represents how it behaves in a circuit. So that's an important thing to grasp. We'll call regular VA without the prime the voltage across the terminals of the antenna. In many instances, especially when you talk about energy harvesting and power transfer, you're not just interested in the power, but you're interested in the magnitude of the voltage, because that tells you something very important about the system. So for example, VA. How do I calculate that in terms of the variables that we've talked about, particularly PR, the received power? Well, if you work through circuit theory, you can find that this is 2 times the magnitude of the complex load times 2 RA PR square root magnitude ZA plus ZL. So put that in your notes because we'll come back to that one in a second. In fact, we'll work a little problem to illustrate something, a useful result. Okay. So let's do our first example. I have a 50 ohm coax. Has anyone ever done any RF test and measurement in your undergraduate laboratory? No, that's okay. That's okay. You know, in RF engineering, they have these standard cables that you always design to. Standard loads, standard cables, standard inputs and outputs. And you always try to keep at a constant impedance. And the reason is if you've got a 50 ohm cable and you've got 50 ohm equipment and a 50 ohm transmitter, then if you stay with the same impedance, everything is matched. There's no reflection. Oh, yes.
Could I ask, the ZA and the ZL are in the same phase?
Not necessarily. They can be different values.
Then why can VA be voltage divided by the absolute value of the impedances?
So VA is just the amplitude of complex VA, right? So we're just looking at the magnitude of the voltage in that equation. And that's why there's no phase information. What the exact phase of that voltage is relative to VA prime, we would need to do complex circuit theory to measure that phase difference.
Thank you.
No, you're welcome. So it's a good distinction because it comes up in our 50 ohm coaxial cable problem. So here's our problem. We've got a 50 ohm coax and there's a 20 dBm signal traveling down the line. What is dBm? Decibels, but what does the little m stand for? Milliwatts. Milliwatts. You're right. You're right. So power in SI units is watts. When you talk about radio waves, lots of engineers like to use the dB scale, or in particular, they'll either use 10 log base 10 of the value in watts, and that's dB capital W. Or, in some instances, especially at the receiver end of things, they will talk 10 log base 10, the value in milliwatts. And that's what we call dBm. So 20 milliwatts, or 20 decibels, dBms, is actually 100 milliwatts, right? Log base 10 of 100 is 2. I multiply by 10, that gives me 20 dBm. 30 dBm is 1 watt. 40 dBm is 10 watts, and so forth and so on. Okay, so then the question is, for this example, well, we answered the first one. How much power transmits down the line, travels down the cable? We already said that that was 0.1 watts, or 100 milliwatts. And then the next question is, how big is the peak voltage? On the transmission line, on the coaxial cable? So in that case, let's go back to our formulas here. When something we know that V squared over 2RL is the power delivered to the load. So if we know what that power is already, 0.1 watts, then we can solve for V squared if we know what the impedance is. In this case, we said it's a 50 ohm impedance line. Now, keep in mind that this is not necessarily a resistive load. We're talking about a cable originally in the problem statement. The impedance of a cable is the ratio of voltage and current that the cable carries in one direction. It's an intrinsic impedance. It doesn't represent ohmic loss the way a resistor does, but it does represent that same V over I relationship. And the power works the same way. The power in that wave is going to be 1/2 VI, or 1/2 V squared over R. So if the impedance of the cable is 50 ohms, then V squared over 100 is equal to 0.1 watts. If I solve for V, I find that the amplitude, my peak amplitude, is 3.16 volts. That's a good, useful number to hang around, right? Because what if I was transmitting 1 watt down a cable, a 50 ohm cable? You'll hear we'll probably use lots of examples with 50 ohms because that tends to be what RF engineers use as their reference value for cables. 75 ohms as well, but generally in microwave engineering it's 50 ohms at the higher frequencies. If I transmit 1 watt, or 30 dBm, 0 dBW, then I basically have, what is that? 10 volts of signal. If I increase the power by a factor of 10 on the same line, I'll get a square root of 10 increase. So I'll get 10. That's when the voltage starts to get kind of large in that spot. We don't usually think about, oh, it's just a watt. But at AC, on a 50 ohm line, that can be a 10 volt signal. In my lab, I have a Magnetron, which is basically, it's a 5.8 gigahertz Magnetron. It's a higher frequency version of the thing inside of your microwave oven. And it dumps, mine dumps continuously 700 watts of power into a waveguide, which I can then collect with a cable and use to drive other pieces of equipment. Do I select just any old cable? Well, no, because according to this equation, V is equal to 2 intrinsic impedance, call it R0, times the power transmitted. This is 2 times 50, 100, times 700, so it's like the square root of 7 times 100. So it's like 250 volts of peak signal. If I'm not careful, I'll actually hit reverse breakdown in some small areas of my circuits with that much power. Not to mention, it's dumping into some circuit at the end of the line where it may be more the power than the voltage that I have to worry about. So anyway, this is just some exercises to think about how to calculate and go between the world of voltage and power and voltage. It's important, especially when we get to transmitted power, because we're not always worried about a really big voltage. Sometimes even a small voltage is very informative and we need to calculate it coming out of an antenna. So I think I have one more example to show. And this will lead nicely into our next discussion. So this is an example from energy harvesting. A silicon-based RFIC, radio frequency integrated circuit, is connected to a folded dipole antenna. This RFIC has an ideal 4-stage charge pump. But we're going to learn that that's a device used for harnessing RF power. And that presents itself as 20 minus J350 ohms. A real value of 20 ohms and then a highly capacitive value of negative J350. Under CW excitation, CW stands for continuous wave, just a sine wave. The antenna receives negative 2 dBm of matched power. So this is our P sub R, not our P sub L. I'm going to put P sub R in parentheses. What is the voltage across the IC? Let's start with that question. This is an important question. Okay, let's figure out how this works. First of all, we've got to compute negative 2 dBm to a useful value that we can calculate with the watts, right? So that's negative 2 dBm of received power. I convert to watts by first subtracting 30. Going from dBm to watts, that gives me negative 32 dBWs. And I take 10, raise it to the power of negative 32 divided by 10. That gives me watts. That undoes the 10 log base 10 operation of decibel log conversion. And if I do that computation, I find this is 0.63 milliwatts. So that's my first step. And the second step is my VIC, the voltage into that integrated circuit, according to the equation that we gave you earlier, was 2 magnitude ZL. Remember that ZL is the 20 minus J350. Divided by ZA plus ZL. I forgot to write down in the problem statement ZA. This is a folded dipole, so it happens to have a lot of impedance, 300 real, and then a little bit of inductive J100. And then you multiply this by square root of 2 PR R sub A. So we know what ZL is, we know what the antenna impedance is. P sub R is 0.00063 milliwatts. RA is going to be 300, that's the real part of the antenna. When I'm done, I find I get 1.06 volts. This is the value of the AC signal that goes into the energy harvesting circuitry, which is a bunch of diodes and capacitors that turn this into DC power. So my next question is, of course, why is this number important? Is this enough for us to harvest the energy? Remember what I mentioned in the previous class period, that a diode has to turn on. What is the turn on voltage of a silicon diode? I think you said 0.7. Yeah, that's the classic doped silicon diode. It turns out you can change the doping and change the turn on voltage, but that's a nice standard textbook value that everybody learns in their freshman or sophomore circuits class, right? Well, that's going to be 700 millivolts, 0.700 volts. Is there enough to actually meaningfully convert in this scenario. If I have negative 2 dBm and an antenna and an integrated circuit connected to each other, does that system pull enough power out of the air? It does. It does. We would consider this to be a fairly decent. It wouldn't be very high efficiency. You know, you'd be lucky to get 50%. But we've got almost 400 millivolts above the turn-on threshold. The efficiency will be less than 50% probably, but we'll convert power. Now we'll get into more of the ins and outs of that in a second, but if it turned out that we had negative 12 dBm instead of negative 2 dBm, it would be a different story. The efficiency tends to fall off the table once you drop below 700 millivolts. So you'd have to switch diodes or get some gain with your antenna or increase your transmit power, or do something to make this system work out better, this far field energy harvesting system. So any questions so far? Okay, so we only have about 15 minutes left in the class period, 20 minutes. So we'll get started on the next unit, and this will be an introduction to energy harvesting. Yeah?
How to get -32 dB?
Oh yeah, so we have -2 dBm. To convert to dBWs, you subtract 30 to get -32 dBWs. The reason is there are 1,000 milliwatts in a watt. And in a logarithmic scale, that's a 30, like adding 30 or subtracting 30, depending on which way you're going. So if I have -2 dBm, I subtract 30 to get dBWs. If I had -2 dBWs, I would add 30 and I would have 28 dBms. That 30 represents 3 orders of magnitude on the dB scale, right? It is very difficult to start thinking in the dB scale, but my guess is that by the end of the class period, you will be dreaming in dBs. You will go to your grocery store and you will think, oh, this is on sale. This is 3 dB off, 50% off. Okay. Now, let me change over to some PowerPoint slides, and I'll put these slides up on the web. Wireless power transfer system. What does it look like? Well, this just looks like a slightly expanded version of what we were drawing in the previous lecture. We got an RF generator, that's our transmitter. Here's an antenna. Here's a receive antenna. And here's what we would call our receiver, our load. And in terms of the RF electronics that go into this, you have a bandpass filter. Usually you want to hone in on the frequency of interest that you're going to convert. You have a rectifying circuit that does your actual conversion to DC, and then a low-pass filter. So now let's talk a little bit more about how those different things look electronically. Now, when I was I think it was a junior in electrical engineering, this was over 20 years ago, we were taught that you can always convert AC to DC power. We do it all the time, right? When you plug something in. So this was the circuit that they taught me how to convert DC power with, or AC to DC power. So I'd have AC coming in here, add an ideal transformer with a turns ratio, usually stepping down because I was going from the wall, which is in the US is 110 volts, or 120 depending on where time of day you measure it, at 60 hertz. 120 volts, 60 hertz. China's like 105 volts. Is it 50 or 60 hertz?
50 hertz.
50 hertz. So, and then you run it through some diodes, just like we're going to talk about. And the structure that they taught me was this thing called a bridge diode configuration. This is in my power class. Okay. Now, in this circuit, they called this a full wave rectifier. There are two extremely big reasons why you would never use this for the type of radio wave rectification that we're going to talk about in this class. Can anybody identify the two issues at hand?
Losses.
Losses, yeah. Where's the lossy part of this?
0.7, 0.7, every time you'll be losing.
Oh yeah, that excellent observation. Give the man a prize. He was he correctly identified. Look at this. This is a bridge rectifier, and the nice thing about a bridge rectifier is it's a full wave rectifier. It's very simple to build. You usually put a capacitor here too, by the way. But really, when there's an upswing, when you've got sinusoidal current coming, and there's an upswing in the current, this diode is off, this diode is on, this diode is off, and this diode is on. So the current goes like this, and then returns through there. Then, let me reset this. Then for the other direction, the other direction is nice because in the negative swing, it's the opposite. The diodes that were on, when you have a bottom swing coming through, voltage, negative voltage across the AC inputs, then this diode turns off, and this diode turns off. No, excuse me, this one turns on. All right. Let's see. Negative means that this is higher than this. So this one turns on. Oh, and yeah, this one would then turn on. So the path through here is like this. These are off. There we go. Now, you're actually turning on 2 diodes per pass, which means instead of losing just 0.7 or whatever your threshold voltage is, yeah, you're losing 1.4 twice. And the problem is when you're dealing with socket power out of the wall, nobody cares. You can lose a little bit of voltage like that and still have very efficient transformation, because this is probably 10 or 15 or 20 volts coming through here. So at RF, when we deal with very low voltages, we usually have the opposite problem, right? We don't have enough voltage to turn our diodes on. And then there's another problem, is that once they turn on and convert, the voltage that we do convert isn't usually high enough to do anything with immediately. So we have the opposite problem. We don't need to step down the voltage, we need to step up the voltage. And we can't do it with the transformer, generally speaking. In some instances you might be able to do it, but this idea of a bunch of windings, coupled inductors with mutual inductance, the idea of doing this at RF is prohibitively lossy. You just can't make transformers efficiently at RF, especially at microwave and higher. It just doesn't work. It takes up too much space, too lossy. And so in this instance, what we have to resort to is a charge pump. Something with multiple stages of diodes and capacitances that store energy, absorb energy, basically charge up capacitors to the degree as much as they possibly can in parallel, and then discharge in series, so that we get the kind of output voltage that we need. And so what we haven't showed here is what do you actually connect to this device? You know, our discussion is going to concentrate today mostly on this. Then here, what you would probably do if you were making a wireless harvesting sensor, an energy harvesting sensor, is put some sort of what I would call a charge management system. Which then interfaces to whatever application. Maybe you're just driving a low-powered microcontroller or some other integrated circuit to do sensing, communications, computation. And the charge management system is basically a way to optimize the power flow through here and possibly merge it with other forms of power. Maybe your device also has a solar cell on it. When the light's out, you got to use only RF. But when the lights are on, you can supplement or switch to a different power supply. Maybe you've got a thermocouple connected to it. You're scavenging heat energy, or a piezoelectric device that's scavenging vibrations. 10 years ago, all those things were ridiculous. They were like, you know, we would think about them and say, well, you could do this, but you know, you need an earthquake to transduce enough energy into this circuit to scavenge energy. But nowadays, things are so low power, you can actually do these things. We talk about just the regular motions and vibrations that our human body experiences. We've had some senior design projects recently at Georgia Tech where people are looking at just the thermal gradient differential between the human body and the air around it. You're talking like, you know, 5 degrees Celsius, right? Not much. And Carnot efficiency says that's a very inefficient thermal process. But you can actually get some useful values out of that. You can drive circuits with that. I've seen it actually work. Occasionally, the Georgia Tech undergraduates do a senior design project that works. It's exciting. Okay. So here, I'm going to finish up with just several different circuits that we use to harvest RF energy. This is the classic half-wave rectifier. It's the simplest possible circuit, and truthfully, if you understand how this circuit works, you pretty much understand how all of them work. Here's your load, your AC is coming in. Unfortunately, this isn't very efficient because it only rectifies the positive hump. That's right. This diode's going to be off for the negative voltage swing. Where does that power go? It just gets reflected. If this were an antenna that you were hooking it up to instead of a pure source, that would just reflect right out of the antenna. You'd lose at least 50% of your power right off the bat. But that first hump turns the rectifier diode on, deposits charge here. Because this acts like a switch, the charge stays here, and it's effectively already converted to DC. The RF input impedance and the mismatch loss, because the diode is a nonlinear device, the actual impedance mismatch loss will vary as a function of amplitude. That's one thing to remember about all of these circuits. They're highly nonlinear. So that means it's going to be difficult to match them. It's going to be impossible to match them for every power level. The other thing to remember too is that the impedance, it's very strange to think about, but this is a DC resistor. How you load this resistance will actually change the RF impedance that you see over here. So even though this is DC at this point, having a really big resistor as opposed to a really small resistor will dramatically change the RF impedance that you see here. Very strange. Now if you want a full-wave rectifier, you just need another diode and another capacitor. So this is the upswing, of course. All these capacitors are chosen in such a way that at DC they're open circuits, but at radio frequencies they're short circuits. So this would go right on through this capacitor, and it would turn D1 off and D2 on and deposit a charge on the upswing of the voltage across that capacitor. Then on the minus swing, what would happen then? Well, this one then turns off, and you get positive charge that deposits on this capacitor. So then the next time when you hit the next upswing, this voltage pushes this charge through, and you get a doubling effect, right? There's already a DC voltage on this capacitor that's up to the peak of this voltage amplitude minus the turn-on voltage of the diode. And then this is sort of riding the voltage to the next level. And so what you find is that your V out max, this is the best possible scenario, is going to be equal to your antenna voltage output minus VT times 2. Turn on voltage. And this is just an estimate. It actually gets a lot more complicated than this because diodes don't act like perfect switches, right? They're actually these kind of square law devices in the region that we're talking about. But this is a very good back of the envelope. We'll use this rule of thumb for a lot of our calculations, and we'll tell you how to do the more exact calculations. Now, if you're interested, there's actually a sneaky way to build these. A full wave rectifier with just one diode. This is a structure called a single shunt rectifier. When you hook it up to an antenna, the rectifier circuit, particularly this rectifier circuit, plus the antenna, we have a special word for that in electrical engineering. We often call that the rectenna. So if you're ever reading a paper or a book on wireless power transfer, when they start talking about rectennas, they just mean the whole thing together is a circuit. The single shunt rectifier, or rectenna, works because on the upswing, well, let's start with the downswing first. You have a downswing in voltage coming across here. That's going to turn this diode on. And where does the charge go? The DC charge is going to go down this transmission line. This is just a wire or an electrical pathway that is electromagnetically significant, quarter of a wavelength in length. But it doesn't matter. To a DC charge, quarter of a wavelength at RF is just a little electrical path. So it's going to travel over here, and deposit across that capacitor. There's nowhere else for it to go at that point. Then on the upswing, what's going to happen? Well, in the upswing, this diode is off, right? And this, we're going to have to, I don't know how familiar you are with transmission lines. This is a quarter of a wavelength long. And that means that the wave is going to take a finite amount of time to travel down, right? So if I wanted to sketch a voltage waveform traveling on this transmission line, it's going to start as a peak like this. And in space, it's going to be, this is lambda over 2, half of a wavelength. The upswing lasts half of a wavelength on a transmission line. But this is the part that enters the transmission line. That leading edge is going to go down. It's going to strike the end of the transmission line. What load does it see at the end of the transmission line? Well, it sees a capacitor. And at high frequency content, or if it hasn't been charged up yet to an initial value, when you hit it with a stimulus, all of a sudden, what does a capacitor look like? It's a short circuit. It accepts it. Charge readily if it's not charged, or if you disturb it. It's only when you make a disturbance and you sit there with that same stimulus for a long time that it charges up and becomes an open circuit. So at DC, this is an open circuit. This is a short circuit. What is the reflection coefficient of a short circuit on a transmission line? Do you remember that from your circuits class? Open circuit has a reflection coefficient of +1. Short circuit has a reflection coefficient of -1. That's right. Which means there's no place for the signal to go. This is shorted out. So by the time you get to the end, a quarter of the wave, let's say half of the wave has made it onto the transmission line. The end strikes here, and all of a sudden you get the opposite voltage reflecting back. So this pulse reflects polarity. by the time this reflects back here, the last of the waveform has entered onto the line, the last of the upswing. So when this guy comes out, what you basically see is the leading edge of a downward pulse. This reflection over here converts this pulse into a backwards pulse, a negative pulse, which then turns the diode on and puts more charge over here. In fact, there's a doubling effect because this guy gets to the end just as the next negative swing is hitting this diode. The two superimpose and you get a doubling effect. So this is going to be very similar. Whatever your antenna amplitude is, minus the turn-on voltage, except you can actually put a 2 in front of here because you're doubling it before you have to turn on the diode voltage. The maximum possible output. Now all these structures are nice, but we've never done more than just double the voltage. In many instances, we're going to have to quadruple or multiply by a factor of 10 to get a usable logic level to drive our electronics. So that's where the charge pumps come in. Here are several different examples of charge pumps. All these are rectifier circuits that are arranged in a way to step up the voltage. And they go by all sorts of different names. This is a classic Dixon charge pump. As the RF drives this system, the voltage steps up through here and you get 2n volts out minus whatever the turn-on losses are. Over here, Cockcroft-Walton, or the Grenadier-Villard. This is just another configuration, and the same thing happens. Basically, the output here winds up being a doubling, or tripling, or quadrupling, depending on how many stages. Yeah. Well, a lot of times they will refer to as a pair of diodes as a stage for your charge pump. And then you can play this game forever. The only problem is that your losses become multiplicative in many of these systems. So there comes a point where you just can't add any more stages. You lose as much power as you're gaining, or you lose as much voltage as you're gaining. And there's another configuration down here. I'm not really interested in, truthfully, there are probably dozens of different ways to arrange these circuits and get some form of voltage multiplication. If you thought about it for a few hours, you could probably come up with your own charge pump configuration. And then you could name it the Dylan charge pump or the whatever charge pump. Yeah.
The 2VA, how I still cannot get why there's a double here.
Why there is a doubling here?
When there's two diodes connecting like this, why it should be double in the output voltage?
Ah, okay. Let me see if I can discard here. So let's pick a circuit. Which one do you want to pick here? Cockcroft-Walton, Dixon, or modified?
The first one.
Dixon? Okay. That's good. So if you look here, let's just look at this segment right here. This segment here is actually just a full wave rectifier, right? It's the exact same circuit from here.
Yes.
There's other stuff connected to it, but we're not going to. If you just look at this part, at least here, I'm going to get a DC voltage out. That's going to be double minus some losses what the input antenna voltage
there's
is.
a double.
So to go back here, what happens is that on the downswing, when it's negative voltage here, you are going to cause current to flow through here and deposit charge onto here. Take it away from here. So this is the path. So right here, this node is going to have a DC value that's about equal to the amplitude of the RF waveform. This is a single, if you just look at this section here, this is basically a single stage half-wave rectifier. So now you're always starting from a DC voltage that's about this value. So the upswing, when the upswing happens and you push charge over here, that charge superimposes on top of the DC value that's already there. So if you got rid of this diode, it would just be a half-wave rectifier. When you put the diode in there, that VA rectifications rides on top of what is already a VA rectified signal, and you get double. Now over here, I've got that exact same circuit, so I know I'm actually going to get a DC value that's twice, let's say I had the perfect diode with 0 turn-on voltage, 2 VA, riding right there. Well now, I've got a voltage doubling circuit here, but it's like I'm biasing this one diode with VA, 2 VA. So now, when my downswing happens, I'm going to put a charge here. That gives me another VA, but now it's actually going to be, in terms of DC, it's 3 VA. And then the upswing will move this over to 4 VA. So it's interesting that the Cockcroft-Walton, this particular topology, really resembles, Cockcroft and Walton were not electrical engineers per se. They were actually physicists that were conducting some high voltage experiments. I think they were building some of the first colliders, you know, where you use a high voltage and you try to smash atomic particles. And their system was actually mechanical. They built a charge pump, and it was literally a bank of capacitors and then these mechanical switches that would switch up and down and basically charge up in a DC capacitor with DC, and then ladder it up. You charge up another capacitor with DC and ladder it up, and it would mechanically step up the voltage. So you could turn a small DC voltage into a very high DC voltage, and then simulate a bolt of lightning, or in their case, I think they were accelerating a particle to a very, very high velocity. They actually won the Nobel Prize for their work. This is like 100 years ago. They didn't have any transistors to work with, so everything had to be mechanical. But the topology of the charge pump still actually bears their name, Cockcroft-Walton. Okay, I think I'm probably over time at this point. Yep, time to end the class. So what we'll do, is everybody okay with watching the videos instead of coming to Friday class? Okay, good. Then what we will do, we'll come back on Monday. We'll meet as a class, and I'll pick up from where I talked about. What we'll do, we'll finish off this discussion on electronics and some of the limitations they have for energy harvesting and really just RF detection. And then we'll talk about link budgets, which is that, I'll review that one component that we still don't know how to transfer energy from. We need to get energy from point A to point B, from transmit antenna to receiver antenna. And then we'll have the whole system. We'll have a working basis for talking about the entire system in either a wireless network or an energy harvesting system or a wireless power transfer system or a backscatter communication system. You'll be able to track the power everywhere. Then it'll get really fun. Okay, see you next class period.